Welcome to our deep dive into microservices best practices. In today's rapidly evolving digital landscape, microservices architecture has become a cornerstone for building scalable, resilient, and maintainable applications. It allows organizations to break down complex monolithic applications into smaller, independent, and loosely coupled services, each responsible for a specific business capability. While the benefits are numerous, including faster development cycles, easier deployment, and enhanced fault isolation, unlocking these advantages truly depends on adhering to a set of robust best practices. Without them, the distributed nature of microservices can introduce significant complexity, leading to operational challenges, performance bottlenecks, and security vulnerabilities. Over the next 10 minutes, we'll explore 9 essential tips that every developer should master to successfully design, implement, and manage microservices, transforming potential pitfalls into powerful capabilities. Let's begin our journey into building truly robust microservice systems. Our first and perhaps most fundamental best practice is to design each microservice with a single, well-defined responsibility. This principle, often referred to as the Single Responsibility Principle, or SRP, dictates that a service should have only one reason to change. In the context of microservices, this means each service should encapsulate a specific business capability or bounded context. For example, an order service should exclusively handle order-related operations like creation, retrieval, and status updates, not customer management or payment processing. Adhering to SRP ensures services remain small, focused, and truly independent. It reduces the impact of changes, as modifying one service for a particular business logic doesn't necessitate touching or redeploying unrelated services. This also significantly enhances clarity for developers, making it easier to understand, test, and maintain individual components, ultimately contributing to a more agile and resilient system. Moving on to our second essential tip, decentralized data management. A common pitfall when transitioning from monoliths is attempting to maintain a single, shared database across multiple microservices. This completely undermines the autonomy of microservices. Instead, each microservice should own and manage its data store, encapsulating its data entirely. This approach, known as database per service, offers tremendous benefits. It allows services to evolve independently without database schema conflicts. Enables polyglot persistence, where each service can choose the best database technology for its specific needs, like a relational database for transactional data and a NoSQL store for analytics, and significantly improves resilience. If one service's database experiences issues, it doesn't necessarily bring down other services. While this introduces challenges like maintaining data consistency across services, patterns like event sourcing and Saga can effectively address these, ensuring true independence and flexibility. Our third best practice emphasizes embracing asynchronous communication between microservices. While synchronous RESTful API calls are straightforward, they introduce tight coupling and reduce overall system resilience. When Service A directly calls Service B, Service A must wait for Service B to respond, and if Service B is unavailable, Service A fails. Asynchronous communication, typically facilitated by message queues or event buses like Kafka or RabbitMQ, decouples services. Services publish events or messages to a broker, and other interested services subscribe to these events. This means Service A doesn't need to know about Service B. It just publishes an event, allowing Service B to process it when it's ready. This pattern significantly enhances fault tolerance, scalability, and responsiveness. For example, an order-placed event can trigger multiple downstream services like inventory update, payment processing, and shipping notification concurrently and independently without any direct dependencies, making the system more robust. Our fourth best practice is to implement an API gateway. As the number of microservices grows, clients face the challenge of interacting with many different endpoints. An API gateway acts as a single, centralized entry point for all client requests, abstracting away the underlying microservice architecture. Instead of clients needing to know the specific addresses of user service, product service, or order service, they simply send requests to the gateway. The API gateway is responsible for several critical functions: intelligent request routing to the correct microservice, authentication and authorization, rate limiting to prevent abuse, caching common responses, and response composition, where it aggregates data from multiple microservices before sending a single response back to the client. This simplifies client-side development, improves security, and enhances system performance and maintainability by offloading common cross-cutting concerns from individual services. It's an indispensable component for managing external interactions in a microservices ecosystem. Next, we have best practice number 5, prioritize observability. In a distributed microservices environment, understanding what's happening within your system is paramount. Observability goes beyond basic monitoring. It's the ability to infer the internal state of a system by examining its external outputs. This involves 3 pillars: comprehensive logging, real-time monitoring, and distributed tracing. Comprehensive logging ensures every service emits detailed, structured logs for errors, requests, and significant events. Real-time monitoring provides dashboards and alerts for key metrics like CPU usage, memory, latency, and error rates across all services. Distributed tracing, using tools like OpenTelemetry or Jaeger, allows developers to trace a single request as it flows across multiple microservices, identifying bottlenecks and failures. Without robust observability, debugging issues in a microservices architecture becomes a near impossible task, leading to prolonged downtimes and frustrated development teams. It's essential for proactively detecting and resolving issues. Best practice number 6 is to automate everything possible. The sheer number of services, deployments, and configurations in a microservices ecosystem makes manual operations unsustainable and prone to human error. Automation is not just a nice-to-have, it's a fundamental requirement for success. This encompasses several key areas. Continuous integration, CI, and continuous delivery, CD, pipelines are crucial for automating builds, tests, and deployments, ensuring code changes are rapidly and reliably delivered to production. Automated testing, from unit tests to integration and end-to-end tests, validates functionality at every stage. Furthermore, infrastructure as code, IAC, tools like Terraform or Ansible allow you to provision and manage infrastructure programmatically, ensuring consistency and repeatability across environments. By automating these processes, development teams can achieve faster release cycles, reduce operational overhead, and significantly minimize the risk of errors, freeing up valuable developer time to focus on innovation rather than repetitive tasks. Our 7th best practice is to design for fault tolerance and resilience. In a distributed system, failures are inevitable, not exceptional. Services can go down, networks can become unreliable, and dependencies might experience latency spikes. The goal is to build a system that can gracefully degrade or recover from these failures rather than collapsing entirely. Key patterns include the circuit breaker pattern, which prevents a service from repeatedly trying to invoke a failing dependency, allowing it to recover. Retry mechanisms automatically reattempt failed operations after a short delay. The bulkhead pattern isolates components to prevent failures in one part from cascading to others. Finally, implementing graceful degradation ensures that if a non-critical service fails, the core functionality of the application can still operate, perhaps with reduced features. By incorporating these strategies, you create a self-healing system that remains stable and available even under adverse conditions, ensuring a better user experience. Our 8th critical best practice is to implement security by design. In a microservices architecture, the attack surface expands due to the increased number of services, communication channels, and potential entry points. Therefore, security cannot be an afterthought. It must be ingrained into every stage of development. This means implementing robust authentication and authorization mechanisms for both external clients via the API gateway and internal service-to-service communication. Utilizing mutual TLS or MTLS for inter-service communication ensures that both parties verify each other's identity and encrypt traffic. Secure secret management through tools like HashiCorp Vault or Kubernetes Secrets is vital for handling API keys, database credentials, and other sensitive information. Regular vulnerability scanning and security audits for each microservice, along with adherence to secure coding practices, are also paramount. By building security in from the ground up, you significantly reduce risks and protect your distributed system from evolving threats, ensuring data integrity and user trust. We've journeyed through 9 essential best practices for developing robust microservices. From designing for single responsibility and decentralizing data, to embracing asynchronous communication, implementing an API gateway, prioritizing observability, automating everything, designing for fault tolerance, and embedding security by design, each tip plays a crucial role. Adhering to these principles transforms the potential complexities of microservices into powerful advantages: enhanced scalability, improved resilience, faster development cycles, and greater developer productivity. While the initial investment in these practices might seem substantial, the long-term benefits in terms of system stability, maintainability, and agility are immeasurable. As technology continues to evolve, so too must our approach to architecture. Continuously learning, adapting, and applying these best practices will empower developers to build truly high-performing, future-proof microservices systems that can meet the demands of tomorrow's applications. Thank you for joining this deep dive. We hope these insights prove valuable in your microservices journey.